Hello, welcome all of you for the next lecture on the properties of the atomic nucleus. So, in the last lecture, we briefly summarized whatever we had discussed in the lecture prior to that as to how neutron was discovered and the results of scattering of alpha particles on various nuclei were correctly interpreted by Chadwick. That was a very great accomplishment. Then after that, what we did was to look at the scattering of the electrons, very high energy electrons actually, on nuclei. This was elastic scattering, from which we extracted information on the radius of the atoms, the size of the atoms. As I told you, at this point we are not too very much interested in finding out the precise shape of the nucleus, so called precise shape, because anyway it is way beyond us at this particular juncture. But if you assume that it is spherical, then you can estimate what the radius is, and you can also estimate what the mass distribution or the charge distribution inside the nucleus is, and we got this beautiful concept of saturation. That is what we found. So, all of it can be summarized in the simple formula as I told you. So, let us call it as nuclear saturation. That the radius as a function of A is given by some constant R naught into A to the power of 1 by 3. And please remember, this A is the atomic weight, so called, but strictly speaking this is equal to number of protons plus number of neutrons in the nucleus. If you ignore minute mass differences between the proton and the neutron, and also minute mass differences because of the mass defect or the binding energy, then A also would represent atomic weight to a fairly good approximation. That is what we did. So, if you know about the size, then the next question is to know about what the masses are and what the stabilities are. Now, to put it in a very simple way, if you do not want to get into too much of a complication, then you can immediately extract what the mass dependence should be as a function of A. So, what are we going to assume? We are going to assume that charge distribution is a constant in the nuclear volume. Of course, it is not exactly a constant. If you people remember, the figure looked something like this. It looked like something like this. So, basically we are going to isolate this particular point, or it could be even this particular point, and roughly call it as the radius of the nucleus, because it is in this region that the charge distribution is a constant, and this is the information that we get from elastic scattering. So, if you also take the neutron distribution to be a constant, so this will imply rho matter is a constant. So, in making this statement, I am ignoring this tapering off. We had a fairly long discussion on that. So, we are going to assume that rho matter is a constant. In that case, we are going to get a relation that my mass as a function of A grows roughly linear with A. So, it will look like m naught into A, because the volume also grows linearly with A. This is a very excellent starting point for us to understand the properties of the nucleus, but as they say, the devil lies in the details, and now what we want to do is to look at the microscopic differences. And that is what I started with. And when we look at microscopic differences, it is important for us to remember that Newtonian mechanics is not going to be important, is not going to be enough for us. What we need is a better formulation, a correct formulation which was due to Einstein, namely the relativistic formula, and I made a brief presentation of what those formulae were. So, what I propose to do today is to take off from that particular point and tell you how to understand, how to interpret the so-called mass dependence, the true mass dependence, not the so-called, the true mass dependence of various nuclides as a function of A and Z. From that we can get information on the stability of the nucleus, energetics of the nucleus, on radioactivity, on fission, on fusion, so on and so forth. In fact, without doing too much of complicated physics or mathematics, if we understand this, we can straight away get a glimpse of what is happening, for example, in the interior of stars, let us say sun. That is one of the great advantages of looking at it rather carefully and slowly. So let us get into that. So that is what we wish to do now. So the lecture that we are going to start today, I have called it as the atomic nucleus. This is the second one in the atomic nucleus, and our main focus will be on masses and stability. So you people should be aware that all throughout we have been speaking of stability. When I worried about the atom, I worried about the stability of the atom. Why is it that the electron is not going to fall off into the nucleus? Why is it that the hydrogen atom is stable? So we had to make use of the uncertainty principle. We have to make use of the Pauli exclusion principle. In a similar manner, we have to worry about the stability of the nucleus. Some nuclei are stable, some nuclei are not stable, and when they are not stable, they get transmuted to other nuclei which are more stable, and the chain goes on until it hits a point which is completely stable. So we want to understand that. So in order to understand that, what we shall do is to first of all spend a few minutes briefly recapitulating whatever I said in the last class, and then proceed to make a detailed analysis. So as I told you in the last lecture, the first observation is that no material particle can move with a speed v greater than or equal to c. In fact, I took some time to tell you the distinction between what I mean by a material particle to distinguish it from something like a photon. There are other particles like a photon, what we call in physics like a gluon or a graviton. You will come across them later. But at this point, when we say a material particle, by that we mean it can be at rest, and when it is at rest, it will have a finite mass, non-zero finite mass. However, although there is a restriction on the speed of the particle, there is no restriction either on the energy of the particle or on the momentum of the particle. So given this, what Einstein did was to essentially solve this conundrum. I want to keep on increasing my energy without necessarily continuously increasing my speed. That is, the speed would increase, but it cannot cross the light barrier. It can never exceed the speed of light. In fact, it cannot even touch the speed of light. That is something that we have. And secondly, in the same way, I should be able to increase the momentum also by keeping v bounded between 0 and c. That is what I want to do. And the solution, the brilliant solution that Einstein gave, was to say that inertia or mass depends on the speed. So this slide collects the relevant formulae that I used. M of v is given by m naught into 1 over root 1 minus v squared by c squared. And this factor 1 over root 1 minus v squared by c squared is many times called gamma. It is the gamma factor. And the v by c itself, so v squared by c squared, v by c itself is called beta. So many times people write m equal to m naught into 1 over root 1 minus beta squared, or simply m naught into gamma. My energy in a similar way is m of v into c squared. Now remember, my inertia is depending on the velocity. Momentum is p of v, m of v into v, and just as you write E equal to p squared by 2m in Newtonian mechanics, in Einsteinian mechanics and relativistic mechanics, you can check that you can write E squared equal to p squared c squared plus m naught squared c to the power of 4. So this figure is important for us, and that is the reason why I am showing you again. You see that all the way up to beta equal to 0.8, that is v equal to 0.8 times the speed of light, my mass barely changes. That is what we are finding. But we should not be misled by this, because although my delta m may be very small, my delta E can be very large, because my delta E will be given by delta m into c squared, and c, remember, in ordinary units has a very large value, 3 into 10 to the power of 8 meters per second. That is to say, in order to create a small mass, you need a lot of energy, or even if you lose a small amount of mass, you produce a lot of energy. There is something that we have to remember, and that is what we are going to use in our discussion. And this is what I summarized in this particular slide with only two equations. E equal to mc squared is of course there, all of us are familiar with it, but c is a universal constant, and therefore we write delta E equal to delta mc squared. This is the most important thing. As I told you in the last lecture, historically Einstein was able to argue delta E equal to delta mc squared, and with great insight he speculated that this delta can be removed and we can write E equal to mc squared. That is, if we go historically, we go from bottom to top, but now what we are going to do is assume this equation and make use of the second relation. That is what we want to do. I think this is where I had stopped. First, I have to establish some units, because for whatever reasons, the physics community, there is something called International Union for Pure and Applied Physics. They have agreed to adhere to a convention, and it has come after many iterations. It is not that we cannot use other units, but it is always good to adhere to convention so that everybody understands easily what we are saying. So what I am trying to tell you is the following thing. The question is, how am I going to denote masses? So when it comes to masses, there is this SI unit which is in the unit of kg. Now this is a very convenient unit when we look at, let us say, the human scale, the weight of a table. How much does a man weigh? Is that okay? Or for that matter, how much does an even elephant weigh? Or if you are buying grains from a grocery shop, how much you are going to buy? This kg is a very good system of unit, and pound is not very different from kg, so you could continue to use that also. But the minute you go to something like atomic scale, when you are looking at elementary particles, or if you are looking at molecules or atoms, electrons, protons, this becomes inconvenient. For example, I do not give you the distance between, let us say, Delhi and Mumbai in units of centimeters. I cannot do that. It is a very inconvenient unit, and probably it is also not a very appropriate unit. In a similar manner, if you have very short distances, is that okay? For example, if I want to know what is the distance between the tip of these two thumbs, if I am going to look at it, I am not going to give it in the unit of meters. Therefore, the units that we employ depend on the natural length scales, time scales and the mass scales that are inherent in the physical system. It is a matter of convenience. So if you remember that, what we are going to do is to start a new set of units, and that is to start with the mass of carbon. So if you look at it very carefully, carbon has many isotopes. I have already given you the definition of what an isotope is. So you take carbon 12 with exactly 6 protons. So we are speaking of 6 protons, 6 neutrons constituting carbon 12. So what I could have done is to either start with the mass of the proton or the mass of the neutron. If you give me the mass of the proton, that fixes the mass of the neutron in the units of the mass of the proton, that fixes the mass of carbon, but that is not what we are going to do. As I told you, for historical reasons, we take the mass of carbon to be the fundamental unit. That is the most important thing. So how do I assign? What I do is to assign 12 units of mass to carbon 12. That is what I am going to use. That is what I am going to say. Therefore, my single unit, that is called as the atomic mass unit, AMU, and that is further lengthened to shortened to U. 1 U is given by mass of carbon divided by 12. That is what I am going to assume. Now if I were to write it in terms of conventional units, whatever we are used to in the units of kgs, that will turn out to be 1.660539 into 10 to the power of minus 15 kgs. That is what we have. So henceforth, we are not going to look at kgs anymore. Is that okay? We know the conversion from the kgs to 1 atomic mass unit. Although I write it as U, It is actually atomic mass unit. Earlier people were using the notation AMU. Now people have shortened it to U. So 1 unit is given by 1.660539 into 10 to the power of minus 15 kg. So from this you can immediately infer what the mass of carbon is. Mass of carbon would be this 1.660539 into 12. So you can estimate what it is. 12 6 are 72, 12 6 are 72 plus 7 79, 12 ones are 12 plus 7 19. That is what you are going to see. It is something like 19.77 whatever into 10 to the power of minus 15 kgs. That is what you are going to get. Once we have zeroed on to this unit, 1 unit is equal to 1.660539 into 10 to the power of minus 15 kg. Now what do we find? My mass of the proton will be given by this number. All of them are expressed up to 6 decimal places, 6 significant digits apart from 10 to the power of minus 15, 1.00727 units, and mass of the neutron is 1.008664 U. Remember, I discussed the relation between the mass of the neutron and the proton when we were discussing Chadwick's experiment. He estimated it to be something like 1.1 times. Then we said that no, there was a 10% error in that calculation. So that is what we have. So for example, if you look at 2 isotopes of carbon, the chlorine, this is here in your exam as an example in an NCERT book. It has 2 isotopes. One with mass number 35, another with 37. Then one with 35 has mass of 34.98. Another fellow has a mass of 36.98. So that is what we have. So this is how the masses look like. Is that okay? And if you know the ratio in which my isotope with 35 and isotope with 37 comes, then I can find the mean mass of chlorine. That is a worked out example in your NCERT textbook. You can verify. But the main message that we have to take from this is that we are going to express everything in terms of 1 atomic mass unit. That is our fundamental unit, and in SI units it has this number. Okay. Now I want to discuss the binding energies. So what do you mean by binding energy? Let us go back to the case of hydrogen atom. What is it that we have? So in the case of hydrogen atom, what I have is, I have the mass of the hydrogen atom, then I have mass of the proton and mass of the electron. If the total energy of the hydrogen atom were equal to the total energy of the proton and the total energy of the electron, then there is no bound state at all. What do I mean by a bound state? By bound state, I mean that assuming that my electron is going around the proton, let us say, as in the hydrogen atom, that is the minimum energy for me to take this electron to infinity. I should be able to take this. If you want, you can even move the proton to infinity in the other direction. And in the other direction, they should be, when they have an infinite distance between them, what is the total energy? What is the binding energy? They should be at rest, and the energy that I supply is given by the binding energy, and we associate it with 13.6 electron volt. So in some sense, the mass defect is 13.6 electron volt. The difference between the mass of the hydrogen atom and the sum of the masses of the proton and the electron is 13.6 electron volt, which is a very, very small number. This is the idea that we want to perfect by making use of Einstein's mass energy relation. So what do? You start with a nucleus, as I told you, X, A, Z. Don't forget that this is my so-called atomic weight. This is my atomic number. In fact, a better notation for atomic weight is Nucleon number. So if you feel like, forget whatever I told you all these days, henceforth we shall only use the word Nucleon number, and Nucleon number means the total number of nucleons, and nucleons include both protons and neutrons, and this is my atomic number, which is the total number of protons. That is what I have. So what I will do, this has Z number of protons and A minus Z number of neutrons. and each proton has a mass mp and each neutron has a mass mn. And what are their masses? I have already given you 1.007 something, 1.008 something in atomic mass units. So what do? What we do is to first find the sum of the masses. So my sum of the masses will be given by Z into mp. So each proton has a mass mp and there are Z of them, and then I will write A minus Z into mn. If Z number of protons and A minus Z number of neutrons had not come together because of the force of attraction, and if they had not formed a bound state, then if you bring them all together, the total mass will still be given by Zmp plus A minus Zmn. But that is not going to happen. What we do is to look at the mass of X. That is what I am going to look at. This X, of course, is labeled by A and Z, which I am not showing, and I look at the mass difference. That is what I have. I say that this nucleus is bound because I have to supply energy in order to remove the protons and neutrons. So what does it mean? If I look at this quantity and I call it as delta m, identical equal to delta m, this must be less than 0. Now we are not speaking of mass, but we are speaking of energy. So I should modify that. So what do? I will say delta m c squared is less than 0 and this is my binding energy. So, and this delta m is my mass defect. Defect means it is wanting. So, because of the force of attraction, my incoming protons and neutrons, they shed some of their energy and they went and sat in this bound state, and if they want to recover their free state, we have to supply that energy, and that is what I have summarized in these two equations. So I write my delta mx, whatever I wrote in this slide, to be Zmp plus A minus Zmn minus mx, that is my this one. The way I have defined here, my delta mx is a positive quantity. If I had changed the sign, it would have been a negative quantity, but my binding energy is always a positive quantity. Therefore, binding energy is given by delta mx into c squared. Therefore, this delta mx is the negative of the mass defect that I defined when I wrote it on the sheet of paper. So that is what we have. Now what is the binding energy? Now binding energy is a rather complicated concept, because suppose you give me a nucleus, or for that matter, suppose you give me an atom, what is it that we do? So this is a very interesting exercise that you can do. So let us start with the hydrogen atom. Let us start with the hydrogen atom. I have my proton, I have my electron. Assume proton to be infinitely massive. We are not worried about that. It is a very meaningful and an unambiguous question to ask, what is the binding energy of the hydrogen atom? And that is simply the energy, as I told you, to take it away to infinity. So you have 13.6 electron volts, let us say. That is what you have. However, if you were to come to helium, for example, so you have the alpha particle as your nucleus, 2 protons and 2 neutrons, and there are 2 electrons. That is what you have. What would you expect the binding energy to be? This is a very interesting thing. For example, if you ignore, let us say, this electron will be seeing the Coulomb field produced by the alpha particle, and you can make use of the hydrogen atom formula and you can immediately write the binding energy for this. But then this electron is also going to interact with this electron, and therefore there is a repulsive energy. Therefore, my binding energy for the first electron, let us say, binding energy for first electron will be whatever the binding energy coming from Bohr model minus repulsion. And where is this repulsion coming from? Electron repulsion. Therefore, the binding energy for the first electron, what do you mean by the first electron? Whichever I remove will be smaller than the binding energy, for example, if this other electron were not there at all. Now, this is my helium, not ionized, neutral, not ionized. Now, what I will do? I will ionize my helium atom. So, what do I have now? I have again an alpha particle and there is only one electron. Now, I can calculate the binding energy of this electron. This is my second electron. The first electron has already been brought to infinity. By making use of the Bohr model, you know how to do that. Therefore, the binding energy required, the amount of energy required to remove the first electron is smaller than the amount of energy required to remove the second electron if I proceed sequentially. This is a problem that we are going to encounter even in the case of nuclei, and in order to not get into too many complications, we introduce a concept, and that is the binding energy per nucleon. One could argue that if I had given two electrons, I don't know which one of them I would remove for the first time. After all, they are identical particles. Therefore, what I will do is, I will calculate the total binding energy. What is the total binding energy? Strip off this helium atom of both the electrons and then divided by 2, that will become the binding energy per electron. In a similar manner, what will be the binding energy of a nucleon? You have to have something like an alpha deuterium, let us say one proton and one neutron, then there is no problem. If you go to helium, then what is it that we have? We have 2 protons and 2 neutrons. So, I will ask what is the energy to remove all of them away from each other to infinity. So, I will get a binding energy. I will divide it by 4, that will become the binding energy per nucleon, and that is a good way of representing. So, in other words, if you give me the binding energy per nucleon, if I multiply it by A, the total nucleon number, that should give me the total binding energy. So, it is more convenient to plot the binding energy per nucleon rather than the total binding energy, and that is shown in this very beautiful curve, which is again taken from your textbook, 12th standard NCERT textbook. And what is it that you find? The most interesting that you find in this is that, of course, you start with deuterium, which has a very, very low binding energy. Then you come to tritium, it has a higher binding energy. Then you go to 4 helium, there is a spike, that is a very important thing. But when you go to 6 lithium, actually the binding energy goes down. Then again it sees a peak in 12 carbon. All these are important numbers for us. What are the important numbers for us? I will tell you. Deuterium is important for us, tritium is important for us, helium is important for us, carbon is important for us. So, that is what we have. And then when you come to 14 nitrogen, it will go, come down again, and 16 oxygen will go up again, so on and so forth. But once you reach sulfur, 32 sulfur, it has hit a plateau, and after that it is roughly constant. You see that it is roughly constant, hovering around something like 8.1 or 8.2 MeV per nucleon. The natural units for discussing energies in the nuclear scale is always million electron volts, just as the natural scale in the atomic scale is always given by electron volts and fractions of electron volt. Of course, if you go to atoms, then can become milli electron volts, so on and so forth. When you do, for example, spectroscopy, etc., we will not worry about that. But the important thing is all the way from 32 sulfur, that is nucleon number is equal to 32, to all the way up to 236, you find it is roughly a constant, except after 100 molybdenum, it starts off slowly tapering down and it achieves a plateau. This is a very, very important thing for us to remember, because this is exactly just the opposite of, for example, what happens in an atom. In the case of an atom, what happens is that as I keep on adding more and more electrons, the electron repulsion will keep on increasing. But here, of course, there is no concept of a core. Atom has a core called the positive core. Here there is no concept. You find that the binding energy is a roughly a constant. And this phenomenon is again what is called as the saturation. In fact, one of the important problems in nuclear physics, on which people worked for many, many years, is to understand this saturation phenomenon. And just as in the case of atoms, you have these inert gases. They are the least interacting, they have the greatest binding energy, obviously for that reason, and they are your noble gases, helium, neon, xenon, krypton, so on and so forth. The analogues of those quantities are, you can see, helium, carbon, oxygen 16 for instance, which show sudden spike with respect to their neighbors. So if you people were to pursue a course on physics later, and if you did a nuclear physics course, you will actually build a model which is very much like the shell model of the atoms, and you will be able to understand that. Of course, there are more complications, but that is something that you can remember about. So this figure is very, very important for us, and let me summarize them in this slide. Okay. The most important point is that it started with a very, very small value, it got saturated and it came down. So whenever a function behaves in this particular manner, apart from these fluctuations, the natural question to ask is, where is the maxima of the curve? And it turns out that the maxima of the curve lies in iron, 56 iron, that is where it lies. So that means you give me all possible nuclei, all the way starting from, let us say, deuterium to a very, very heavy nucleus like a uranium or a polonium or whatever, which contains about 200 and odd number of nucleons. Is that okay? The maximum energy that you have to supply per nucleon, if you want to completely dismantle the nucleus, is iron. So what do you conclude from that? You would conclude that of all the nuclei, iron is the most stable of nuclei. Iron comes in many, many isotopes. Remember what is isotope is? Isotope means what? The same Z but different value of A. That means you have added or removed a few neutrons, but you have kept the number of protons fixed. That is what you have done. So iron is the most stable nucleus. Actually silicon is also fairly stable, close to that. It has not been shown in this particular figure. So what I would like to do is to ask you people to remember this fact that iron is the most stable nucleus. We do not have an explanation for this at this particular point. We will take it as an accepted fact. Although some explanation can be given, qualitative description can be given as to how the saturation takes place. So this is something again that I have summarized in this particular slide. So iron 56 has the largest binding energy, it is about 8.75 million electron volts. It is roughly constant in the range 30 to 170 MeV, and it has smaller values for both small a and a greater than 200. So if you were to invert this, in terms of the minimum energy, what is going to happen? The maxima would become minima, and these quantities will go to the top, and purely from a viewpoint of stability analysis, everyone would like to go and sit in the state of iron. So eventually you should sort of imagine that the whole world will be consisting of some big iron lattice, let us say. That is what you would imagine. Of course physics is much, much more complicated, but there is a nice picture to make. That is what we have, and it has smaller values for both a small and a greater than 200. That is something that we have to remember. A small means what? I was speaking of lithium, boron, beryllium, carbon. Okay, after that things are going to change. These are the things that we have to remember. Now I cannot do a quantum mechanical calculation at your level. In fact, even if you knew quantum mechanics, it is not going to be easy for me to actually work out these things. So what I will do instead is to try to make some qualitative statements. That is the most important thing. I will try to make some qualitative statements and see how much I should be able to extract from these qualitative statements. Is that okay? That is what I would like to do. So let us see what it is. We spoke the language of protons and neutrons. So let me come back to my slide and tell you a few interesting things. So if you remember, my protons are positively charged and neutrons not charged. In fact, I can be very, very careful. Positively electrically charged, not charged electrically. I will tell you why I am using the word. Its electric charge is 0. That is what we have. For your information, although neutron is not electrically charged, it has a magnetic moment. In terms of nuclear Bohr magnetons, it is given by minus 1.91. Okay, it has a magnetic moment. So, if I pulled a bunch of protons, let us say, pulled a bunch of neutrons and pulled a bunch of protons and neutrons together, their interactions would be completely different. This will be very, very strongly repulsive, whereas here this will be weak. Why will it be weak? Because they interact only through the magnetic moment, and magnetic moment forces, how do they go? They look like 1 over r cubed, whereas the repulsion goes like 1 over r squared. That is what I have. And if you put protons and neutrons again, all the protons will repel each other very strongly. The interaction among neutrons will be very, very small. Interaction among the protons will also be very, very small. So, if this kind of a situation had persisted in the case of nuclei also, then the concept of a binding energy per nucleon would have been meaningless. But that is not what happens. What happens is what I have collected in this slide. So, I should probably start with the second point. All protons are bound to each other with the same strength. So, what is the operative important word here? Bound. If it were electromagnetic interactions, they cannot be bound. They are going to repel each other. That means my protons not only participate in electromagnetic interactions, they also participate in a new interaction, a new kind of interaction, which I will call as the nuclear force. And what is the nuclear force? That has to be attractive. I am going to qualify this statement in the next slide, so don't take it with complete seriousness. So, I will become a little bit more careful. Inside a nucleus, my protons are bound with the same strength, and neutrons are also bound with the same strength as the protons inside a nucleus. But then, since protons actually are positively charged and they should be repelling each other, what do we conclude from this? Nuclear forces are much stronger than the Coulomb repulsion. So, when the two protons come close to each other of the order of 1 Fermi, and how much is a Fermi? 10 to the power of minus 15 meter. There is an enormous Coulomb repulsion. You can work that out, but my attractive nuclear force more than compensates that repulsion. Okay. But then, in that case, I should be able to bring lot of protons and neutrons together and make very, very big objects. It doesn't happen. I am at most able to make about a nucleus with about 200 atomic nucleon number. That means the interaction distance, the range between of the nuclear forces must be very, very small. Let us say of the order of a Fermi again, of the order of a Fermi, femtometer, maybe 1 femtometer, 2 femtometer, 5 femtometer, because if you have a to the power of 1/3, cube root of 100 is not a very big number, because 6 cubed is already something like 200. So, the nuclear size is only 6 times larger than the original nucleus. So, they are short ranged, and that short rangedness is also suggested by saturation. The binding energy roughly remains the same. What does it mean by that? Let me explain to you and tell you a few more subtle things that are important for us. I have not written down in the slide, but I am going to explain that to you, and these are interesting aspects nuclear forces. Let me list them for you. Number 1, nuclear forces are strong, that we have seen. But 2 is not a point but a question. Are they always attractive? This is very, very important for us. And what is the answer? No. This is something that we have to remember. So, you have to listen to this carefully, because otherwise whatever is there in this slide would become completely misleading. So, let us look at the periodic table. You have hydrogen consisting of one proton, then you have 2H1, which is one proton, one neutron, and what is it called? Deuteron. Then you have 3H1, which is tritium, which is one proton, two neutrons. Then I am going to make a list of some more nuclei for you. For example, you have 3 helium consisting of what? 2 protons, 1 neutron, and then of course you have the very stable nucleus, 2 protons, 2 neutrons. You look at 12 carbon 6 protons, 6 neutrons. That is what you have. Similarly, I can write one more, which I do remember. After that, I will have to look up some data. So, if you look at, for example, oxygen 16, 8 protons, 8 neutrons. These are very stable. But on the other hand, for example, if you look at something like 235 uranium, this has only 92 protons. So, 92 protons, I hope I am correct. And what will be the number of neutrons? So, 235 minus 92, 143 neutrons. So, what I would do is to invite you people to look up the periodic table, look at the data of how A and Z are distributed, and you will find the following things. There are roughly equal number of protons and neutrons. Number 1, that is something that you should look at. Number 2 that you should look at, as A increases, so let us say beyond 100, number of neutrons is more than number of protons. As A increases, the binding energy per nucleon also decreases, therefore they are not all that stable, and most stable nuclei have equal number. Like helium or 12 carbon or oxygen, so on and so forth. And what is the most dramatic thing? I have to write that. Most dramatic. No nucleus with only protons, no nucleus with only neutrons. You need both protons and neutrons to form a nucleus. What do you conclude from that? So, what we conclude from this is that the nuclear force between two protons is repulsive, very important. The nuclear force between two protons is always repulsive, just as the electromagnetic force between any two protons is repulsive, number 1. Similarly, the nuclear force between two neutrons is also repulsive. But I told you we have deuteron, it has a binding energy of something like 4 MeV or some such thing, or maybe 2.5 MeV. So, but force between a proton and a neutron can be attractive. Can be attractive, and this is a very, very important feature for us. And if you want to model it as an interaction, then you have to very carefully assign the appropriate nuclear charges. They are much more complicated than what you would imagine at this point. Let me not get into that, and you have to build a theory. So that is what it is. So what I am trying to tell you is that this periodic table, what is there in the periodic table and what is not there in the periodic table, tells us that there is a lot of food for thought, and still, even though we are not able to get a completely satisfactory theory of how nuclear phenomena works, is that okay? By looking at energetics, we should be able to actually get a fair idea of understanding what the processes are. So that is the whole thing. So that is what I have summarized in this particular slide. So it is in some particular order, but now I hope you people will understand these statements in the correct perspective. Neutrons are as strongly bound to protons in the nucleus. Protons are bound to each other with the same strength because of the existence of the neutrons. Nuclear forces are much stronger. Saturation suggests that nuclear forces are short range, and most important for us, the energetics for understanding relativity, fusion and fission is completely supplied to us by what? By the periodic table, by the great figure that I showed you, namely the binding energy per nucleon curve. So this is a curve which merits a very good, a very deep and a careful study, and that is what the community of nuclear physicists has done, and that is something that we have to remember. So let me repeat for you. Please read this statement. Protons are bound to each other with the same strength, must be interpreted very, very carefully. They are bound to each other with the same strength in the sense that the binding energy per nucleon is the same. That doesn't mean that two protons attract each other via nuclear forces. It is a kind of an abuse of language, because people say nuclear forces are charge independent. That means an entirely different thing than what we would naively, unthinkingly assume, and that is the reason why I am giving this clarification. So these are the questions that I would like you to ponder about, because I don't have time to get into that, but I have already given you some kind of a qualitative answer. So the question is, why is there no proton-proton bound state? Why is there no neutron-neutron bound state? And why does the number of neutrons become larger than the number of protons with increasing A? So these are the questions that attracted the attention of a whole lot of people, starting from, let us say, 1920 to 1900. Even now, people are doing very sophisticated calculations to understand nuclear structure and nuclear reaction. Is that okay? And two good examples are lead 208 and this must be uranium 235 uranium. You see, the number of protons is much smaller than the number of neutrons. So please correct it. This is actually U and not PB. This is a transcription error. A complete understanding of the nuclear forces, you might be interested to know, is a $1 million question. Normally, the word $1 million is used in a figurative sense. You know, you say, do you think that this person will come for the meeting today? We say it's a $1 million question. By that we mean we don't know the answer. But in this case, it's literally a $1 million question, because there is a very celebrated prize called the Clay Prize, actually Millennium Prize. If somebody can answer the problem of nuclear forces completely, starting with any fundamental particles, you must have heard of quarks and all that, then that person will become extraordinarily famous and also rich. And what are the crucial features? It depends on electric charge. It depends on nuclear charge. I gave you an idea of what nuclear charge is. It is a strong interaction. It is probably something like 100 times or 1000 times stronger than the electromagnetic interaction, and it is of a short range. And what is the range of these interactions? It is about a femtometer. This is the takeaway from the binding energy. So here is a figure which illustrates what the binding energy is that what the potential between, let us say, a proton and a neutron is. I have called it as a nucleon-nucleon interaction. At very large distances, there is no nuclear force. They have shown it up to 2.5 Fermi. It is almost dead. But if I switch on the Coulomb force, of course, it will be there. But even the Coulomb force goes to 0. At very short distances, it actually becomes repulsive. Is that okay? This repulsion is not entirely due to the Coulomb repulsion. Actually, even the nuclear forces can have something called the hard core, and then you have a valley. So this is something like, the van der Waals force. You must be familiar with your molecular forces, which you would have studied. Is that okay? And my electron, my proton and neutron try to come and sit in this minima. Classically speaking, of course, you can have any number of bound states between a proton and a neutron. But by uncertainty principle, it cannot sit here. It will have to sit somewhere here. And if you look at a deuteron, there is only one energy state that is allowed, because my deuteron does not have an excited state. So this is some kind of a cartoon or a picture for the potential that is acting between a proton and a neutron. But please don't take it very, very seriously. It is only one part of the interaction that is indicated by one yes, not. I will explain to you what it means qualitatively. Just as electromagnetic forces are dependent on both position and momentum, because my magnetic force depends on my momentum, my nuclear forces also depend on position, momentum, and whether it is a proton, neutron, or what their isospin is. Isospin is the analog of the nuclear charge, and also on angular momentum. They are also angular momentum dependent forces. They are very complicated, but then this is a cartoon, if you feel like, at this particular point for you to get an idea of what the interaction is. And what you should notice is that it is hitting a peak around 0.5 Fermi, 0.5 femtometer, and it is getting saturated, let us say, around 2.5 Fermi, which is about 2.5 femtometers. So the size will be of the order of a femtometer or whatever. That is what we have. So this is something that we have to remember. Okay. Now all this time we have been very, very qualitative. Now is the time for us to make it quantitative, because physics, after all, is the science of numbers. It is not numerology, but what we do is to give principles, we make it quantitative, we convert them into numbers, and the experimentalists verify them, and based on the experimental results, either the theory is confirmed or it allows us you to propose a better theory, so on and so forth. So now let us start looking at some numbers, and I would advise all of you, urge all of you to go back and work out many such examples. You don't have to necessarily look at problems at the end of your class book text or anything. Pick up the periodic table and start working them out. It is a great joy, let me assure you, and let me show you some numbers. As you can see, I am being quite fussy because I am keeping numbers to up to a very large number of significant digits, and that is not because my calculator gives me values up to that many points, because as I told you, very, very small changes in mass can give rise to very large changes in energy. That is something that you have to do. So let us start looking at the mass of the proton. My mass of the proton, as I told you, is 1.007276 atomic mass units. My neutron is slightly heavier, 1.008664 atomic units. So later you will see that purely in terms of stability, my neutron must be less stable than proton. The question is, my neutron can become a proton. In fact, it does happen. That is what is called as the beta decay. Let us not get into it now. Then you have my helium, which is 4.002602U. These numbers, you should note them down and you should work out. Now, how do I calculate the mass defect? Very simple. I look at the mass of the helium atom. Okay. When I say mass of the helium atom, I mean 4 helium. Is that okay? 2 protons, 2 neutrons, the most stable isotope. So if you look at it, then you have mass of the helium minus 2 into Mp plus Mn. There are 2 protons, there are 2 neutrons. So I add the masses and multiply them by 2. and lo and behold, what do I get? The total mass of the helium atom is less than the combined mass of what? The protons and the neutrons that constitute the atom. And how much is the difference? The difference is minus 0.029278 U. That is what I have. Okay. Now I compute the binding energy for that, and what do I get? The binding energy is simply given by delta mc squared. Okay, this is the energy defect. If I multiply it by minus 1, it becomes the binding energy, and this turns out to be minus 28300.7 keV, or convert it into MeV, it is minus 28.3 MeV. So what do I mean by that? I need to supply 28.3 million electron volts to rip apart a helium nucleus. It's an enormous number. You get the point, right? To rip apart an electron from the hydrogen atom, you needed how many? You needed 13.6. If you want to rip apart two of them, sorry, it's not 13.6, it will be 13.6 into 4, some such thing. 13.6 into 4 is what you will get, because my Z is equal to 2. If you want to rip apart two of them, roughly it's again of the order of, let us say, 200 electron volts or 100 electron volt. But here we are speaking of million electron volts. You have to supply a lot of energy. And that is the reason why it is very, very difficult and hazardous to build nuclear reactors, etc., etc. I will come to that in a minute. Now that means, given the right conditions, the operative word is right conditions, because I have to prepare the right physical conditions. If you bring two protons and two neutrons together, they should prefer to form a helium atom. But it is easily said than done. Why is it so? Because these are short range. So let me explain to you what is happening. So let us say I have two protons. So I should write probably like this. So let me use some other one. So this is a proton, this is a neutron, and let us say all of them are at rest at infinity, and I start bringing them together. Okay, the interaction between neutron and neutron proton, you don't have to worry. But when I start bringing them together, I experience Coulomb repulsion. And my nuclear forces will not operate unless R is of the order of a femtometer. That means there must be enough energy that I should initially supply such that my protons are able to approach each other at 2 or 1 femtometer, and once they reach there, no problem at all, the nuclear forces will take over, and what do I get? I get a nice attraction, of course in the presence of the neutrons. These are very, very important. So if you look at that, I can draw some kind of a effective potential. How will the effective potential look like? My effective potential will look something like this. So I come from infinity, my thing goes on increasing. At some point it becomes attractive and it comes here. This is an effective potential in the presence of the neutrons and protons, all of them, and this distance will be of the order of a Fermi. And at this point my Coulomb repulsion is very, very powerful. Actually it is very, very strong. I ask you to plug in the numbers and find out what it should be. Even better, what I would ask you to find out is, if you are given a gas of protons, proton gas, what is proton gas? Ionized hydrogen atom, is that right? If I am giving you that, at a certain temperature T, you can ask the temperature at which the kinetic energy will be able to bring them to such a close distance. So we want to write 3 by 2 kT is E squared over R, 1 over 4 pi epsilon naught, and this R is 10 to the power of minus 15 meters. Okay. So whatever I was telling you, I have written it here, so you can look at it. Is that okay? What I have is that I have this figure. Is that okay? I have this figure where up to this particular point I am going to get a Coulomb repulsion, and from this point my nuclear force is going to take over and it becomes an attractive force. That is what is going to happen. And I told you that if I had hydrogen atom, what is going to happen is that I would have to equate the mean kinetic energy with this, and you will find my temperatures to be of the orders of thousands of Kelvin. In fact, it should be of the order of 10 to the power of 8 Kelvin. It could even be 10 to the power of 9 Kelvin, and this is something that we have to remember. So what we have done is to argue that if the protons and neutrons come sufficiently close to each other, they will form a bound state. But then to bring them so close is very, very tough. You people must have heard of tokamaks or fusion reactors, so on and so forth. Is that okay? So if you remember that, they try to actually make a fusion of these quantities, which is very, very tough. But then we can always ask, are there such reactors, are there such processes taking place in nature where I can actually bring them together and produce a helium atom? And what is the great advantage? Since the mass of the helium is smaller than the mass of the constituents, I will be liberating energy. So if that is the viewpoint that you have to take, and if you look around, indeed there is such a thing, and that is nothing but your sun. So what I am going to do is to spend the next few minutes describing the dynamics of sun and show how this simple fusion process producing helium can actually explain many, many aspects of energy production in the sun. Sun was a great mystery for thousands of years. Even after the advent of Newtonian mechanics and thermodynamics, it was a great mystery. So what we will do is to start discussing the physics inside the sun with whatever knowledge we have obtained by simply looking at the binding energy curve for the atoms. So let us get into that. So here is a beautiful picture from NASA, which is courtesy Wikipedia, and you find here that sun is a very complicated object, very, very big, of course. We will come to that here. So what is it that you find is, what is more important for us is this core. This core occupies about 20% of the area of the sun, which is very important for us, and the temperatures are enormous. It is of the order of 10 to the power of 6 Kelvin, and the pressure is very, very large. So I want you to remember this picture at this particular point. What we shall do is, starting from here, look at how the temperatures and the pressures are large enough for the fusion process to take place, and explain how sun as a star is able to shine very brilliantly. That shall be the topic for the next lecture, and let us stop at this instant. Okay, goodbye.